Check it.
Okay, welcome back. Today we're going to be continuing the operations that we do on radicals. Today is dividing. So we've done multiplication, we've done adding. Now it's time to divide. Okay, so the first thing we have here is a radical with a fraction inside. So it's division within the radical, actually. And what you do with division inside a radical, or the radical of a fraction, is first thing you do, you try to reduce the fraction to lowest terms. Now this is already reduced to lowest terms because they have no common factors, right? This is 5 times 5, and this is 7 times 7, so nothing cancels out. So you try to do that first just to make the problem easier for yourself. And then here's the main step. The main step is now split this into two separate roots, one on top and one on the bottom, and then evaluate from there, and you're done. Okay? Now the important thing is that you don't have any radicals left in your denominator. So let's say, for instance, that you did this and you ended up with something like this. A radical in the denominator is an irrational denominator, and you're not allowed to have irrational numbers in a denominator. So getting rid of any radicals in the denominator is required. It's called rationalizing the denominator. We're going to be doing that in a few minutes, but I just wanted to point that out. As long as you don't have a radical in your denominator, then you're good, okay? As long as everything else is simplified. Okay, let's take a look at the next one here. So for this one, we have a fraction inside the radical. And like I said, you want to simplify whatever you can simplify inside the radical first, just to make things easier. So let's see what we can do about simplifying this fraction here. Well, 16 over 36 will reduce, all right? A 4 goes into 16, a 4 goes into 36. And if you divide the top and bottom by 4, you can get 4 over 9. Right? That would be 16, 36 reduced to lowest terms. And here you have x to the 4th divided by x to the 8th. What's going to happen is you're going to get x to the negative 4, right? When you subtract the 4 minus the 8, you get x to the negative 4. And you'll flip it down to the bottom. You'll end up with x to the 4th on the bottom and nothing on the top. Okay, or another way to look at it is divide this by x to the 4th, it goes away. Divide this by x to the 4th, it becomes x to the 4th. And here you have y to the 8th and y to the 12th, okay? It becomes y to the negative 4th, which means y to the 4th on the bottom here. Or you can look at it as dividing the top by y to the 8th, and that goes away. Dividing the bottom by y to the 8th leaves you with just 4 left, like that, okay? So doing all that sort of thing leaves you with this fraction here. Once you've simplified, you can now break this into a separate radical on the top and a separate radical on the bottom, like that. The top becomes 2. The bottom, when we chop it up, becomes 3x squared y squared, and we're done. Okay, so that's one way to do it. Now, I simplified before I did the root. You can also simplify after you do the root. Under certain circumstances, it would actually end up being just fine. Like, for instance, if I decided to do the roots first, let's say I broke this up the way it was. So I'm going to do this again, but a different way here. Let's say I broke it up before simplifying. Okay, like that. So separate root on the top, separate root on the bottom. This will still work out. Most of the time, simplifying first leads to an easier question, but I think in this case, it might actually be the same or maybe a little bit easier to do it this way. So the reason why is because 36 and 16 are both perfect squares. That's the reason why. So 16, when you square root, it becomes a 4. X to the 4th, when you square root, becomes x squared. And y to the 8th, when you square root, becomes y to the 4th. On the bottom, 36 becomes 6. X to the 8th becomes x to the 4th. And y to the 12th becomes y to the 6th. And now you can simplify. The 4 over 6 becomes 2 over 3. You have an x squared, actually hold on a second. You have a 2 over 3. X squared divided by x to the 4th is x to the negative 2. Y to the 4th divided by y to the 6th is y to the negative 2. And of course you have to get rid of your negative powers. And the way you do that is by flipping things that are with negative powers down to the bottom. So now you have a 2 on the top, a 3 on the bottom. This x squared flips to the bottom, becomes x squared like that, and this y squared flips to the bottom, becomes y squared like that. You get the same answer, okay? So whether or not you you think that this was easier or this was easier. Like I said, most of the time, simplifying the fraction inside, if you can, makes this part a little bit easier. And notice that we didn't actually have the negative powers. All right, so just two ways to do the same question. Okay, in this section, we're going to be rationalizing denominators. Now, what does that mean? A denominator of a fraction is a place where you're supposed to have a simple rational number. You're not supposed to have, like for instance, here's a fraction. In the bottom of the fraction, what you're supposed to have here is just a simple number, okay? It should be like 5 or something like that. It should not be, for instance, another fraction. And it should not be a negative number. Now you might say, well, why not? Because if you have a negative number, this should be -3/5. The negative would be outside of the fraction, not in the denominator. And this should not be any irrational number. An irrational number is anything that's not rational. For instance, like 3i. Imaginary numbers are not rational numbers. They shouldn't be in the denominator. And we learned that back when we learned imaginary numbers, that we couldn't leave them in the denominator. And radicals, okay? Any kind of a root, whether it's like a third root of 7 or a square root of 2 or anything, any radical in the denominator is an irrational number, okay? Unless it's like the square root of 25, which is actually just 5. So if it's not a perfect square, any radical, okay, is irrational. And you can't leave that in a denominator. That's the rule. So how do we take something like this and rationalize the denominator, okay? How do we get rid of this denominator here? Well, not get rid of the denominator, but make it not a square root anymore. Make it something without a radical. Make it a simple number, okay? And the idea is, well, it's a square root of 2. And the easiest way to make a square root not be a square root anymore is to square it, right? To multiply it times itself. So if you have the square root of 2 and you square it, it becomes the square root of 2 squared, which is just 2, all right? Because the square and the square root cancel out. Now, I have a radical 2 here. I can't just square the top and the bottom. That doesn't work, by the way. If you are thinking, hey, I can square the top and the bottom, that's not going to work this way. This won't work. Because when you're squaring a 3, you're multiplying by another 3. And when you're squaring a radical 2, you're multiplying by a radical 2. And you're multiplying the top and bottom by different things changes the value of the fraction. So that doesn't work. But if you multiply the top and bottom by the same thing, that's okay. So I want to square this bottom, not by actually squaring it like this, but by multiplying it by another radical 2, like this. Now, if I do that to the bottom, I must do that to the top. That creates a fraction here, radical 2 over radical 2. Any fraction over itself equals 1, right? The red part equals 1. And that's okay, because you're just multiplying this black fraction by a 1. Okay, this whole red fraction here is nothing but a 1. And when you multiply by 1, you don't change the value of the original fraction. So what do you get? Well, radical 2 times radical 2 is 2. Okay, because if you think about it, radical 2 times radical 2 is radical 2 squared, and that just becomes a 2. Or you could think of it as radical 2 times radical 2 is radical 4, which is just 2. Either way. Square root of 2 times itself is just 2, and 3 times radical 2 is 3 radical 2. Now, you might think that this looks more complicated than the original fraction, but this one is rationalized. Look at the bottom. The denominator is a simple rational number, whereas here the denominator was a root, right, which is not allowed. And that's rationalizing. So in this first example, we only had a single radical in the denominator, single square root, and it was pretty simple. You just multiply it by the same root, top and bottom, and you're done. But it gets more complicated as the fraction gets more complicated. So let's take a look at another one now. Here, okay, the denominator is not one single term. It's actually a binomial, 2 terms, something plus something, all right, or something minus something for that matter. And doing that trick that I showed you a moment ago, where you just multiply by the same square root, it doesn't work. Watch. If I do use the same square root, radical 3 here, okay, because there are 2 things here, you have to distribute. You can't just, multiply one thing and not the other. So you end up distributing this to this, and now your denominator is 2 radical 3 plus, and then these 2, radical 3 times radical 3, radical 9 becomes a 3. You end up getting that, and the top becomes this. Okay? And you can see you didn't solve the problem because you still have a radical in your denominator. So that didn't work. So that trick only works, okay, that method only works if you have one thing in the denominator only. Here you have two things. So the method for two things is different. The method for two things requires you to use a conjugate. Okay? And this is very similar to imaginary numbers. When we had two things in the denominator and one of them was imaginary, we used the conjugate to get rid of the imaginary. Okay? Like for instance, if we had 2 plus 3i in our denominator, we multiplied by 2 minus 3i, right? When you multiply conjugates, all the imaginary stuff goes away and you end up with, let's see, 2 times 2 is 4, and this is negative 9i squared, which is plus 9, so you get 13. You get a number and no more I. So a similar thing is going to happen here, okay? We're going to use the conjugate of the denominator. Here's how it goes. We're going to multiply this by a fraction. The top and bottom will be the same, but we're going to use the conjugate of this. So this is 2 plus 3i. We're going to use 2 minus 3i, which is the conjugate. And to keep it balanced, we have to do the same thing to the top and the bottom. Now, when we do this, this whole fraction is just a big old 1. And multiplying the black fraction times a 1 will not change the value of the fraction, so it's legal. We can do that. Let's see what happens. So we're going to multiply the bottom. We're also going to multiply the top. The top will be easy because the top is just distributing the 5, right? Distribution of the 5. 5 times 2 is 10. 5 times radical 3 is 5 radical 3, but there's a negative there, so it's minus 5 radical 3. There you go. That's the top is done. The bottom, you have to do the full FOIL, right? You're going to have to go 2 times 2 and 2 times radical 3 and radical 3 times 2, and then you have to do that whole thing. But here's the thing about conjugates, though. Conjugates, the middle two terms always cancel out. That's the whole point of conjugates. So because the middle two terms cancel out, the only ones that survive are first times first and last times last. This is the only time you can get away with this shortcut, right? Usually you have to do, first, inside, outside, last, whatever. First, outside, inside, last. You have to do all 4 steps of FOIL. But you can get away with just F and L, first and last, if you have conjugates. So 2 times 2 is 4. Square root of 3 times negative the square root of 3 is negative 3, right? Because radical 3 times radical 3 is 3, like I explained it before. And there's a negative there. So you get that. And now you can see that this is all going to be over 1. And anything over 1, you can just drop the over 1 part, and here's your answer. Box your final answer. Okay? So conjugate will do the trick whenever you have a binomial, 2 terms in the denominator here for square roots. Okay, let's try another one. So here again, once again, we have 2 things in the denominator, a binomial, something minus something in this case. And we're going to do the same trick. And it doesn't even matter that both of these are 2 roots. Like last time there was 1 square root, right? There was 1 square root here. And this time we have 2 square roots. It doesn't matter. The conjugate still works. So what's the conjugate of this denominator? It's the same thing, but with a different sign in the middle. So if this is a minus, the conjugate will be the same thing, but have a plus instead. And if we want this fraction here to be worth 1, so that it doesn't change anything, we have to do the exact same thing on the top. Now this fraction, because the top and bottom are the same, is like having 3 over 3, or 5 over 5, or any number over itself. It's going to equal 1. So this is something over itself, it equals 1, and that's not going to change the value of the original problem, so we can do this. All right, so let's go ahead and multiply. So it's going to be this times this. Now, the bottom are conjugates. We chose it that way. So that means we don't have to do the full FOIL. We can just get away with going first times first. Radical 3 times radical 3 is 3. And last times last, radical 5 times radical 5 is 5, but one of them is negative, so minus 5. Okay, very easy when you're multiplying conjugates. On the top, however, even though they are identical, they're not conjugates, right? Conjugates are only when one sign is different than the other sign in the middle. These are both pluses. These are literally identical. So you have to do the full FOIL. They're not conjugates. There's no shortcut here. So we're going to distribute all of this. We're going to go distribute to 3 first. So radical 3 times radical 3 is 3. Right, because it's radical 9, right? Radical 3 times radical 5 is radical 15. 5 times radical 3 is 5 radical 3. And 5 times radical 5, well, it's not radical 5 times radical 5. It's Oh, I just realized they're not identical because there's no radical on this one. It's 5 radical 5. So you have that. And you look at these, okay, 15, if you try to break it down, is just 5 times 3. Neither one of these has a square root, so you can't break down 15. 5 and 3 are both prime, so they're not going anywhere. So really the only thing left to do here is just subtract 3 minus 5 on the bottom here. And we get a negative 2 on the bottom here. And the top is going to be 3 plus everything that's up there already, basically. Now, I said before, you shouldn't have a negative inside of your denominator, okay? Like, that's something that you'll get dinged for in pre-calc and calculus. Right now, we'll leave it there. Technically, what you're supposed to do is get rid of this negative. How? Well, you factor out the negative from the bottom and from the top. And what that's going to do is create a positive 2 on the bottom, but all the top ones will become negative, like that. Or another way to do that is to just put the negative in front of the fraction here, like that. And then the top can remain the way it is, like that. But to be honest with you, you know, we're not going to worry about this in Algebra 2 so much. So as long as you're done here, as long as you don't have any radicals, you're rationalized, it's okay. Negative 2 is a rational number. It's just considered kind of bad, you know, hygiene or something like that to leave a negative in the bottom like that. Okay, let's go on to another question here. All right, so now we have the root of a fraction, sort of like we had earlier in the lesson. This one's a little bit more complicated. Now, what I said before was that you try to reduce whatever you can reduce inside first. There's nothing to reduce here. 75 over 4 cannot be reduced, and a over x, and none of this can be reduced. So just go ahead and split this into 2 roots, top and bottom, right? So the top is 75, a to the 4th, b to the 1st. The bottom is 4 square root, 4x to the 7th, y to the 12th, okay? And the way you do each one of these, we already know from previous lessons, you just chop it up. So you got the square root of 75, the square root of a to the 4th, the square root of b, over the square root of 4, square root of x to the 7th, square root of y to the 12th. Now 75 is not a perfect square, so we do a factor tree for it. 75. Well, I think most people, when they think about 75, they think about 25 times 3. 25 is a perfect square, so and 3 is a prime number. If you get a perfect square times a prime, you don't have to go any further. So I'm going to start over here. This 75 becomes square root of 25 times the square root of 3. A to the 4th, when you square root it divided by that invisible 2 here, get a squared. And this b is to the first power. And first power will not divide by this second power here. So the invisible 1 does not divide by the invisible 2. It's too low, it's below it. If this number is below this number, you leave this alone, because the only thing you can do is come down, right, to get to divide by 2, and you can't come down from 1 to divide by 2. You're already below 2. So this is just going to be a square root of b. Radical b will remain like that. Now on the bottom, this becomes a 2. Nothing to break down there. But this 7 right here, this x to the 7th, won't divide by 2. So what we'll do is we'll break it up into x. You come down, right? If you can't divide, you come down 1 power at a time. So x to the 6th will work. But now you need an x to the 1. We don't write the 1, but there it is. 6 plus 1 is 7. And this one here, when you divide by that invisible root of 2, it's going to be y to the 6th. So let's keep simplifying now. This here, square root of 25 becomes a 5. So you have 5, and you have an a squared. That's 5a squared inside, now that are outside of the radicals. Okay, so that takes care of this. That takes care of this. Now what's left? Radical 3 and radical b, you put them together into one radical, radical 3b. Okay, now down here, you got a 2, right? So that's gone. You have a y to the 6th. And this right here, by the way, this is going to be x to the 3rd. That's the whole reason why we broke it off that way. X to the 3rd. So you have 2x to the 3rd, y to the 6th. Okay, so that takes care of that and that. All you have left is this radical x here. Okay, so this is our answer so far. Now, it's all good except for the fact that there's a radical in the denominator. Is this multiple terms? No, it's one term. If it were multiple terms, it would look like this, like 2x cubed plus this, right? Like that's two terms right there because there's a plus or a minus separating the terms. But this is all one big term, okay? So when you have a single term, that trick that I showed you in the beginning where you just multiply by the radical still works, okay? You don't need to use a conjugate. So in this case, all we need to multiply by is the same radical that's in the denominator that we're trying to get rid of, which is radical x. And of course, you want to do it the same on the top and the bottom so that this whole fraction equals, you guessed it, 1. Right? That's the whole point. So what do we get? Well, multiplying the top, nothing really changes. I mean, the 5a squared is still the same. But radical 3b times radical x, well, 3bx. You're just introducing an x up there in the radical. Down here, the radical x and the radical x, the square root of x times the square root of x just becomes an x. And that x, when you add it to this x to the third times another x is now x to the fourth. So this becomes 2x to the fourth, y to the sixth. That 4 is a little too big to be a power, so let me make it smaller. And that's it. Okay, the denominator has no radicals in it. That means it's fully rationalized and everything else is correct. Okay, we are done. I'll see you at the next video.
Check this.